kind of did that, and I'm not going to do the whole thing, just the sort of non-trivial part of it. So, can I follow along? So, the problem is like this, right? So, we have a stage with two resistors. So, VCC is 5 volts. This is 5 kilo, 1 kilo volt, right? And I say VB on is 0.7, VC on is 0.2, VA is infinite, beta is infinite, okay? So the first question is, well, I have two outputs here. The question is, which one is the inverting output, which one is the output, the non-inverting output? Well, we said that if, you know, what kind of stage you have is a function of where the input and outputs are, right? So from here to there, you have a common emitter, right, with emitter generation. From here to there, you have the common collector, you have an emitter follower, right? So this follows that because the VBE drop, pretty much, and this basically goes through an inversion. So this is an inverting output, this is non-inverting output. So it's what are the gains, right? So we gain from here to there, is simply we know you can use the rule we have, right? We said it's minus alpha total resistance in the collector divided by the total resistance in the emitter. And since I have an infinite VA, RO is infinite, so I don't have to worry about that. So this becomes, the total resistance in the collector is 5K, or I can write it as RC, divided by RE plus alpha RM, which is, at that point, which, let's say what the DC level is. Okay, a DC bias of 1 volt. So I said DC level is 1 volt here. So if that's 1 volt, what is this voltage? If this is 0.7, this is 0.3 volts, right? So what is the current? It's 0.3 volts divided by 1K, that's 0.3 milliamps, right? 0.3 milliamps, what is GM? GM is IC over VT, 0.3 milliamps over 25 millivolts, whatever that is. It's 1/3. 12 or something? 12?
1, 2, 3.
I'm sorry?
It's like 1, 2, 3.
Okay, of 12 millisiemens. So if you can plug that in there basically, right? So it's something like, and then calculate the ratio. So if you do that, I think it's something like minus 4.6, which makes sense, right? It has to be close to a little bit less than 5. Because if you didn't have the Rn, it would be 5 to 1. Gain of 5. It's gain a little bit less than 5. And again, from here to there, again, it's the voltage divider ratio between this resistor and this resistor and that resistor, right? So it's going to be Re divided by Re plus alpha Rn. Whatever that is, I think it's 0.9. Okay, so that's it. Those are the small signal gain. Now the other thing is that then the tricky part was the large signal transfer function, right? What happens when you go from so V in, V out? Okay. So now I start from 0. Let's start from 0. If this voltage is 0, transistor is off, right? There's no current flowing. This voltage is VDD. Now it takes at least 0.7 volts to turn it on, according to the simplified model. So it's going to be a DC VDD 5 volts up to 0.7 volt. And then when it starts turning on, right? It starts turning on, and I know, for instance, at 1 volt, I have a 0.3 milliamps, and 0.3 milliamps through 5K, what is that? It's 1.5 volts, right? So this voltage drop would be 1, so for instance, I know at 1 volt, this would be 1.5 volts below 5 volts, so it's basically at 3.5 volts. So it starts dropping, and this slope is basically close to 4, that gain, right? Minus 4.6. So at that level, it's like that. Now, I have to start, as I increase my Vn, this voltage starts dropping relatively fast. So at some point, I have to worry about this diode here, right? And that getting forward biased. So basically, the way I've defined it is, if I say the VBER is 0.7 and the VSAT is 0.2, it means that it takes 0.5 volts for this to turn on, right? 0.7 minus 0.2. Now, that means basically when this voltage becomes 0.5 volt greater than that voltage, right? So how do I determine that? Well, I know at 1 volt, the output is 3.5 volts. So if I raise it, basically, let's say I go to 2 volts, just for the sake of argument. Well, let's make it something simple. I say 1.7 volts. At 1.7 volts, right? This is a 0.7 drop. This is 1 volt. What is this current? 1 milliamp. If the transistor was in a forward active region, this should be 1 milliamp. If it were 1 milliamp, what would this voltage be? 0. So it says that it's down here, but that would be much lower than the 1.7 volts. So it has already saturated. So that can't be a valid point. So it happened before then. Now, how do I determine where it happens? Well, one way is there are many different ways. One way is basically by knowing that this slope is kind of large, and then I say, well, it happens when the V in, at that point, V in minus 0.7 is going to be V out, right? Where it happens. If I draw that line, right? Wherever that crosses this line, that's where it happens, where it goes into saturation. Now, once the transistor goes into saturation, I know that this voltage and that voltage will be only different than 0.2 volts. Different, right? They will follow each other. So what happens is that from that point on, I know this point is a 0.7 volt below that. Right? So from that point on, this will track, V in and V out will be tracking each other at 0.7 volt difference. But now I have to add a 0.2 to get to the output. So I just add a 0.2 here. It will track like that. So, clean it up a little bit. Looks like this, the transfer function. So here I have a slope of minus 4.6, and here I have a slope of 1, or a little bit less than 1. And then, of course, the other one, the transfer function is just basically, from here to there, that's always 0.7 drop. So it's kind of like, looks like that. The other, to the non-inverting output. Looks like that. And then, of course, if you know this, then you put the sine wave in, that's going to be straightforward, right? Basically, you just need to map it. And if you have a sine wave like that, the output will look like, kind of track it here, and then just go crazy like that. It's a one-to-one transfer function from that point. Okay. Yeah, of course, I mean, I know how it works exactly, so I don't go down any wrong paths. That's why you can do it quickly. But, but that's what it is. The tricky part of it was the fact that the transistor could go into saturation. And that's, I tried to give you a hint by saying that, I think I said something like hints. Hint, be mindful of operation in regions other than forward active region, FAR. But that's actually how you can get a non-monotonic response. It's not a great way to get a non-monotonic response because there will be a huge base current at that point. Okay. We can do some of the problems later on if you want, but I think we should have a solution. Any other questions? All right. So in that case, let's go to a slightly different topic now. Related topic. So now we know how to bias things, but one of the interesting things that happen a lot is when you're trying to make an integrated circuit, many times you want to have a differential input, but you want to have a single-ended output. The most common example is an op-amp. If you think about a typical op-amp, there's a differential input and a single-ended output. So the question is, how do I make a stage that has a single-ended input and differential output effectively? So you ask me, well, what's the big problem? If you have a differential here, right? And you had the differential output. Now if I just look at one of the outputs, it would be a single-ended output. So what's the big deal? There's no big deal, that's true. I mean, you can always use that as a conversion of a differential voltage to a single-ended voltage. But what's the problem with doing this? Yeah, you're losing half of your gain. So what is the gain? Actually, what if I define V out over the differential V in, VID? What is the gain in this stage, for instance? VO over VID. What would the gain be? Yeah, 1/2 GMRC. I can use some sort of an active load, let's say. And now when I say be biased, you know that I can generate that, right? This what this really means is something like this. Mirror here connected to some IRF that you know how to generate. Okay. Okay, but so let's not worry about this for now. And think about this. So in this case, what is the gain? What is the gain of this stage?
1/2 GM R out.
1/2 GM R out. What is R out?
It's the output resistance of this.
ROP in parallel with RON, right? It's 1/2 GM RON in parallel with ROP. Okay, fine. So it's a higher gain, but still I'm losing half of it. Doesn't matter, right? I mean, just I have to work harder to get the same gain that I needed before. So one question is, how can I recover that gain, that lost gain? How can we think of a way of using that other lost half? Well, I'm generating this current here, right? So what happens is that when I have a VID here, I generate a GM VID over 2, right? And minus GM VID over 2 drive current, right? On both sides, current being pulled out of these nodes with different polarities. And each one of them basically is pulled out of a similar resistor, here RON parallel ROP, but I'm not using this one. Now the question is, somehow, if I could take this current and replicate it here to drive that node 2, I could take advantage of the second half of the game, which I'm losing right now. How would I do that? Can you think of a simple way of doing it? This is what I need. I need a box, okay, where I draw a current, IX, it pushes that IX out somewhere else.
Not the thing that you had before, or an earlier problem.
Right, it has a name, right?
I can't remember.
That's a simple thing. No, but do I need the voltages to be equal? I actually don't want the voltages to be equal. It's even simpler than that. It's just a current mirror, right? So I can copy this instead of having this load, because this load is completely useless here, right? So I could remove that and turn it into a current mirror. And replicate it. So if I do this, what happens is that I'm pulling this current out of here, so it pushes this current in, which is GM VID over 2, right? That current is being pushed into that node, right? Is it fair to say that this current being pulled out is equal to this current with the opposite sign being pushed in? Right? Just change the polarity and the sign. So now, when I do something like this, both sides, both of these are pushing current into that node. Right? So if I want to determine the voltage of that node, what do I need to do? These two current sources are in effect in parallel driving that resistance, and the total resistance is RON in parallel with ROP. Right? So that's what is that's driving. So in other words, you can think about it this way. VO is this contribution, which is GM VID over 2 times R out, which is RON in parallel with ROP, plus GM VID, the upper part, over 2 RON in parallel with ROP, which gives me GM RON parallel with ROP. And if I want to calculate the gain, basically VO over VID, that's it. That's what it's going to be. Right? So I have basically two signal paths in this case. One is through here, the output. The other one is through here, the output. Now, what is interesting about this topology is that these two paths are not symmetrical. Right? If you were to guess which path is slower, which one would it be? The left path or the right path? The left path, right? Because it has to go through two extra devices. So it's actually a slower path. So there's a And next quarter, when we talk about the response, the frequency response of this thing, we'll see that this has a significant impact on it. And what it does, it actually generates the zero in the transfer function. And there's a pole associated with mirrors called a mirror pole. We'll talk about those. But now, from a low frequency perspective, this was the way of regaining recovering that half of the gain that was lost. So I'm back to GM all the way to kind of the ROP. Now, how about the DC level? So this is kind of a small signal perspective. Let's look at the kind of a large signal perspective and see what kind of DC level I expect to see in this thing. So here, let's say, redraw that state. Okay. I want to ask you kind of a relatively simple question. What is the DC level of this node? If there's no input, if the input is completely balanced, there's no differential level. It's only a common mode fixed level. Both the inputs are at the same level. Can you tell me what that output voltage is? Well, how do we determine that? Yeah, okay, well, so let's sure. Well, let's say beta is large. Let's not worry about beta for a second. Beta is large, so this base current is insignificant. But so how do we determine what is it? Yeah. So let's see. Let's try to see how we find out. So let's write the equations for these two devices, right? What I know is that their two VBEs are equal, right? So what is this current? Let's call this IC1, and let's call this IC2. IC1 is based on this. If this let's call this VBE1 is IS e2 VBE1 over VT 1 plus the VCE of this guy, right? Over VA. Correct? That's the expression we have. What is the VCE of this guy? It's VBE. The way it's connected is just VBE on. It's divided by VA. Right? Now, how about IC2? IC2 is IS E2, again VBE1, they share the same VBE. 1 plus, now this is, let's say, V out minus VDD minus V out over VA. That's this voltage. Okay, so I know that. But what can I say about IC1 and IC2? Let's say beta is large, so don't worry about this current. If the stage is balanced at the input, they have to be roughly the same because they're determined by the VBEs, right? Of these guys. So if they're roughly the same, let's say if these two are equal, this guy cancels that guy, this guy cancels that. And what you're left with is that 1 plus VBE on over VA has to be equal to 1 plus VDD minus V out over VA. So what can you say about the V out? I claim V out is at VDD, or I'm sorry, VCC, VCC minus VBE on. So this voltage is approximately around the same voltage as that node. It's the VBE below VCC in a balanced case, when the input is balanced. Right? And so that makes sense. It's not exactly though. It's not exactly at that voltage. Why not? If you actually go and put it in spice, you will see that it's around that voltage, but it's not exactly the same as that voltage.
Base current.
Base current, yes. Exactly. This current creates a little bit of an asymmetry between these two. The IC1 and IC2 are not exactly equal. Even if these two currents were exactly equal, these two currents will not be exactly equal because this one has this extra component. Okay, so, but if that's the case, then so I know approximately where it would be. And now, what if I ask you, what is the common mode rejection of this thing? How not exactly symmetrical, I mean the way it is. But I know one thing, I've determined that if in a common mode case, I only have a common mode signal. Right? So the stage is already balanced. If the stage is already balanced, we argue that these two voltages are almost the same. 0. What is 0? Okay. No, it's not 0. Okay, let's forget it. So, but let's see what we have, right? So this voltage is the same as that voltage. Okay? So if these two are always the same when the stage is balanced, is it fair to do this? For common mode input. They're the same, right? Like a short. So if I do that, then it becomes symmetrical. Because I can redraw this in this form. And then this becomes the axis of symmetry. Okay. And of course I have to, well, right now, you were actually right. If I didn't have a tail resistance, it would be 0. The common gain is 0. Now I would have an RE. In that case, you're right. Okay, so now I have this RE. So from an AC perspective, when I do, I'll do the same thing that I did before. I break it, split it into 2 RE. Right? Like that. And then I can basically break the equivalent half circuit to something like this. So this becomes 2 REP. And then I have a diode connected PNP up there. Right? Now I have 2 of, so for each half, that's what I see. Okay? So what is the gain? So if this is VIC, VOC, what is the gain of this thing? How would I calculate the gain of this?
Total output.
Right, I have to see what is the resistance, right? Okay. What is the resistance you see when you look into a diode connected transistor?
R over G.
R over GM, yeah, exactly the same thing. So RM or 1 over GM. Okay? So the gain is the ratio of RM divided by, well, 2 REE plus alpha RM. Let's say RM plus 2 REE. Okay? Times alpha, doesn't matter, right? Because beta is large. So A common mode. The common mode gain is that. Which I can rewrite also as by multiplying the numerator and denominator by GM is 1 plus 2 GM REE. So it's actually quite small, right? Which is good, because we want the common mode gain to be small. And we know the differential mode gain, we have already calculated that. A differential mode was GM RON in parallel with ROP. So if I ask you what the common mode projection ratio is the ratio of the differential mode gain, the common mode gain, it's going to be GM RON in parallel with ROP times 1 plus 2 GM RE. It's quite large because this is a kind of a GMRO thing, and this is a plus GMREE, which is the output resistance of another transistor, which would be on the order of RO. So basically, it's kind of like a GMRO and a GMRO. So it's a GMRO squared kind of thing, which is quite large. So it has a reasonably good common mode projector ratio. And it's a good stage to convert a differential to single end. So, in a way, this is the simplest op-amp you can make. Of course, it has some serious problems as an op-amp if you use it like this. But that could be the core of a basic op-amp. And then we can expand on it. And we'll do that. We'll make an op-amp in a couple of lectures. We'll make a whole op-amp based on things we've done. Yes?
Can you say why is that symmetrical again? The common mode part?
Say again, why is it symmetrical?
Yeah.
Because basically I said, well, if I don't have a differential voltage here, right? This voltage and that voltage, we didn't have this, right? These two voltages were the same. As long as this voltage, there's no differential voltage. Now if I apply common mode signal, there's no differential voltage, right? So these nodes go up and down together. And therefore I said, well, if these two voltages are always the same, I can short circuit. So I said, well, I can basically short circuit them like that, and then it becomes symmetrical. Just for the common mode signal. Now, you can do exactly the same thing in MOSFETs. with a MOS in a MOS differential pair. And we can quickly do that. The MOSFET pair would look like this. And then, of course, if you want to convert the differential to single-ended, then you can use a MOS current mirror. And you can see, a lot of things are very similar. They're kind of they're parallels of each other. So you can do exactly the same thing here. And the idea here is that, well, again, what is the gain? If I ask you what is the gain of this stage? Well, think about it. If you were to apply a differential signal, VID, you can look at half of the differential signal applied here and the other half applied there. So this one generates a current which is GM VID over 2. And this one, because this is minus VID over 2, minus GM VID over 2. And this current is going to be still GM VID over 2. Or I could look at it and change the polarity and say, well, this is plus. So both of them are injecting current into this node. Now the question, the gain is determined by what the impedance of that node actually is. Now, this R out, it is the parallel combination of ROP and RON. Therefore, the gain, the total gain, which is defined as VO over VID, is going to be minus GMN RON in parallel with ROP. The same thing as the bipolar case. And again, the same thing, you calculate the common projection ratio and all those things will be exactly the same. Now, let me talk about something else before we go forward. We have a few minutes. And let me ask you the question, in general, if you were to make a current amplifier, how would you make it?
Current mirror. Yeah.
One way to make it is a current mirror, right? I mean, it may not be a very good way. We'll see other better ways later. But if you wanted to come up with one way of doing a current amplifier, I could make a current. So let's say I have a current source, right? I want to amplify. So let's say it's an AC current source, IN. And I want to amplify this current, right? How do I do that with a current source? Well, I need to make a current source, a current mirror here. And then this can go into some whatever the load is. Low impedance load, let's say. Right? So this is I out. And if I make this into a current mirror, I can do something like that. Now, I also need to make, see, this may go negative, right? So this may, if it's just a pure AC thing, this may be positive and negative. So I need to maintain a constant bias current. So I can have an I bias, which is constant. And on top of that, I have this AC signal applied. The same way that, you know, if I wanted to apply an AC voltage, I put it on top of a DC level for biasing. But for current sources to add them, you have to put them in parallel. So now, is this an amplifier the way it is? No. If these W over L ratios are the same, this just replicates that. Now, how can I make it an amplifier?
You can change the W over L.
Right, exactly. You make it n times larger, and then you copy that current down here. So this becomes I bias plus I in times n. Okay. This sounds like, does it sound like there's any limit to this? This sounds like free lunch, right? I mean, say again?
Not at the moment.
Not at the moment. That's a good answer. That's a good answer. Not at the moment. So, can I make this n 10 to the 10? Well, of course, there will be some physical limitation. Of course, the transistor becomes so large. But other than that, I can make it quite large, right? At least in theory. So what would be the limiting parameter here? What would be the manifestation of the whole free lunch principle?
Frequency.
Say again?
Frequency.
Frequency. Well, okay, cutoff frequency, right. So let's think capacitance larger and larger and larger and larger. Yes, it will still be a current amplifier, but it will work up to, if you make it a million, it will probably work up to several hundred hertz. And again, we'll talk about this frequency response things extensively next quarter, but I just wanted to give you an idea of this is not completely free. So what we did here, we also used we did a current mirror, so we did a one-to-one. Somebody may come back and say, why didn't you do an NW over L here? Or W over L? Because in that case, this would be N times that. Right? So this, instead of this, becomes 1/2, becomes 1 plus N over 2 times Gn RON in parallel to ROP. Right? You could do that, right? I'm getting some additional gain here. And this half gets multiplied by N. If you set N to 1, that reduces to this old result. And it does do that. I mean, you can actually make something like this, but you have to keep in mind, this was your slow path. If you do this, you make it even slower. So it stops working the way it's supposed to much earlier. But if you want to make something that's very low frequency, you probably can do that. At some point, you can actually throw away this guy anyway. Because that part's not contributing a whole lot to you. You don't look convinced. Something. No. Okay. How?
It's a free.
Completely wrong with that.
Quick question.
Yeah, sure.
So does that mean people do adjust the size of the transistor in that respect to some extent then? Or
Yeah.
do they just not do that at all?
Right. Well, this is not a very good current amplifier in general. I mean, you will see better ones next quarter when we talk about the frequency response. But yeah, but you can use it as some basic current amplifier. But as you pointed out, I mean, there will be some limit to how much you can get, how much gain you can get when you go through this. Right? You don't want to get a ratio of 1 million, for instance, right? You want to have some reasonable ratios. The other thing you can do, you can actually keep doing this. Right? So, and that has a slightly better trade-off than just a single one. So if I take this, instead of taking my output device, now I take it into an NMOS mirror, and then go to another PFET mirror, right? Like that. I can do this. Let's say this is the W over N, this is N, W over L. So this is W over L, this is N W over L, this is W over L, this is N W over L. So that gives me N to Q. Right? So now, what I can do, I can make each one of them the cubic root of what I needed before, and therefore these are not huge ratios, so the capacitances don't become incredibly large. So let's say I'm trying to get a ratio of 1,000, right? Amplification ratio of 1,000. I could get it out of 1,000, 1 to 1,000, 1 to 1,000, and the capacitance would be 1,001 times that CGS, right? So let's say 1,000 times the capacitance. But now, if I make it out of 3 tens, it's a 10, 10, 10, this is 11 CGS, this is 11 CGS, this is 11 CGS.
Then you have 1,000 times DC current also.
Right, yes. Yes, correct. Of course. But, and again, as I said, this is not the best way to make the current amplifier. But it's a simple way to think about it. Just, I wanted you to think about this ratioing, though. That ratioing is a very powerful concept, particularly in biocircuitry, because there you don't care too much about the frequency response, but it's a low frequency thing. So you can make all sorts of ratios. Up, down, yes.
So would stacking transistors in have the same effect? Or like, can you just put transistor?
You mean you make them cascodes? Or
No, like put them side by side so they're sharing the same.
In parallel.
in parallel?
Yeah.
Where? Here?
Yeah.
Oh yeah, it's the same thing.
So
You can- yeah, because you think about it, right? I could make this out of, let's say, multiple transistors in parallel, right? And all of their gates are shared, all of their sources are shared, so all of their CGSs are in parallel. So it's another way of doing the same thing, exactly. Okay. Any other questions on this? Okay, so that's fine. Next time when we some numerical examples, and then we'll start talking about how we can drive loads. We'll start talking about how we can use the stages to drive loads, the output stages and all that. And then we'll go toward making an op-amp. So we'll make an op-amp, like in a order of putting everything